70, that's perfect. It's that.
That's beautiful.
No, it's like I felt the gator. It's like moving. I didn't really.
Okay. We are going to begin our new topic for real today. All right, but before we get started, I just want to point out to you, if you did not get that email or did not read your email, so you now have on Brightspace a membrane potential activity that is worth 10 points, which will be added into your exam grade, just added straight on top, kind of like extra credit if you complete it. So what that link in the assignment will take you to is a copy link for this slide set, because if 70 of us edit this at the same time, it's gonna get real messy real fast. So what this is shows you different ions that we have typical concentrations of in our body. You also have their equilibrium potential, as well as their intracellular and extracellular concentration. You're going to go through and do a drawing and little explanation for 3 of these ions. You can pick any 3 you want. For each drawings, I started you out with a slide where you're going to put in the ion name, so whichever one you chose, put on the concentrations inside and outside the cell, write in your equilibrium potential. And then I want you to draw me some arrows indicating the CDF, the EDF, and the electrochemical driving force. Okay, so once you do that, you're going to give me a little written explanation of why you drew them the way you drew them, how you figured that out, how you made your choices. Okay, and at the end, I made you a little calculator for the direction of the electrochemical driving force. So basically, you're going to use this to go back and check your work. So you can just change whatever you need to on here. So I'm going to change this to -70. And change this drop down menu to whatever you want. It should tell you the direction of the flow. Make sure I got my code right. Okay. So you're going to use that to check yourself. And if you're still having trouble with the concept of the electrochemical driving force in that direction, I want you to run through as many examples using that calculator as you can until you think you kind of figure out how it's working. Here are my tips for what you should be paying attention to as you do that. So things that are going to make a difference for determining that force, as well as the rules we went over in our last unit. Finally, when you complete this activity, you're going to submit a link to your copy of the slides, and you're going to give me a short explanation for your interpretation of the equilibrium potential, how comfortable you were with this content at the end of the last unit, so before we started the stuff now, and any particular things that you found really difficult to understand about this.
Just for the calculator part, other than checking our work, there's nothing we need to add on with that.
You don't have to do anything. No.
Okay.
Yeah. Okay. Other questions about this activity? Okay, cool. So I will take a look at your slides and reflections. Give you till I think 5 p.m. tomorrow. So you'll have this afternoon tonight to do it, or tomorrow if your schedules are more free. Hopefully, most of you took a quick look at that stuff either right after the exam or yesterday, because we are going to be talking about some of those concepts today. So if you're still fuzzy on those at the end of today, go ahead, do that activity, come back to this content, make sure to ask questions, because this is going to be the basis to how our neurons work. Questions at this point before we start talking about our membrane potential of neurons? So, when we're talking about our resting membrane potential, resting membrane potential is a term you'll see applied to like the resting state of a neuron. So a neuron is like a nerve cell, okay? So they're all gonna start out at rest. And what we're gonna be charting as we think about neurons firing, right? So neurons sending signals, we're gonna be charting changes in the membrane potential. So changes to that, like essentially like electrical difference across our cell membrane. So that difference in charge between the intracellular fluid and the extracellular fluid. When I say resting membrane potential, I'm telling you this is our baseline for the neuron. Then we're going to see changes from that in order to send signals with our nerves. So that's where we're starting here. Now the resting membrane potential for a neuron is approximately -70 millivolts, which is why I kept using that number as our example in our last unit. Okay, might as well start where we need to actually understand the concept. So our resting membrane potential, so VM indicates membrane potential. It's measured in millivolts. Okay, so resting membrane potential of -70 millivolts. Okay. We can compare that resting membrane potential to the equilibrium potential of the two ion species that are really going to make a difference here. So we have our equilibrium potential for sodium drawn on. So equilibrium potential for sodium, basically the membrane potential that sodium would like to create for that cell. So sodium would like the inside of that cell to get to 60 millivolts more than the extracellular fluid in order for its electrochemical driving force and chemical driving force to even out and be in opposite directions. Whereas potassium, our other really important ion for understanding the function of neurons, has an equilibrium potential of -94 millivolts. So it's pulling in the other direction. Our potassium ions want the inside of that cell to get to -94 millivolts relative to the outside of the cell, relative to that extracellular fluid. Okay. Now, as you can see on this little line, our resting membrane potential of -70 is closer to that equilibrium potential for potassium. So potassium is closer to getting what it wants from this situation. Okay. This is because our membrane of our neuron is more permeable to potassium. So potassium is better able to cross that membrane. Okay. So keeping in mind the slide. Okay. 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 We're going to have an interactive question. I need to install on every computer. Okay. So you should be able to, if you can see it, scan that QR code or join at slido.com with this number 35554167 and make your votes for this question. We want to know for this neuron at resting membrane potential of -70 millivolts. I want to know what direction that driving force, that electrochemical driving force for sodium is, and what direction that electrical chemical driving force for potassium is. Wait, get some answers. Another couple seconds. Okay, great. So half of us about are on the same page right now, so let's talk about that. Great. So what we were looking at, we had our resting membrane potential, Vm, equals -70. -70 millivolts. And we know from that previous slide and also some of our examples in our last unit that our equilibrium potential for sodium is +60 millivolts as well. And our equilibrium potential for potassium is -94. So for the first part of this question, okay, starting at rest, so we're first going to think about that sodium. Okay, so we're thinking about a cell, -70 inside. We're thinking about that equilibrium potential for sodium is +60. So sodium wants to move in whatever direction changes the inside of that cell to get closer to +60. In order to do that, sodium is a positive ion. Okay? So every time sodium moves somewhere, it takes a little bit of that positive charge with it. If we want to get from -70 to +60, sodium has to move in, right? So we would have to move positive charges in to the cell to make the inside of that cell more positive. Okay, so that gets us to the first part. All right, so we had into the cell, okay, so most of us got that far. Then we need to think about our potassium. For potassium, thinking about the same starting situation. So we're still starting with a membrane potential, okay, -70. But now we have an equilibrium potential for potassium of -94 millivolts. So just like sodium, potassium is a positive ion, still positive, still going to take that positive charge with it wherever it goes. It wants the inside of that cell to go to -94. Okay. So to do that, right, we're going to need to take some positives out of that cell, right? So as positive charges leave the cell, it gets more negative. Okay, so that is how we know that the electrochemical driving force for potassium out of the cell. Questions, because really this is the main point that we're trying to get to with this whole lecture. So we're going to keep talking about this, but understanding this point will really get you most of the things we're talking about today. Let it sit for a second. We'll also do some Q&A sessions with this app that we're trying out. So as you're thinking, if you have questions, I think you can put them in here and then people can upvote if they have the same question. So let it work. Okay. So here we're looking at a cell at that resting membrane potential of -70 millivolts. Okay. So what we're looking at are the channels that allow that movement. Okay. So we can see we got some sodium here in red. Okay. So sodium is red here. And we can see that sodium is highly concentrated outside the cell in that extracellular fluid because we have our sodium potassium pump pushing it out. So we can see that happening right there. And here on the bottom side of the cell, we can see an open sodium channel allowing sodium to move into the cell. So green arrow means that's our passive direction. So that's going with its electrochemical driving force in the direction it prefers to move. So this would be an example of essentially facilitated diffusion. Okay. On the other side, we see the reverse, right? So on the other side, we can see our potassium ions, which is the sodium potassium pump, is essentially traded for the sodium, right? So the potassium is going the opposite direction from the sodium. Okay, so potassium is moving into the cell when this pump works, okay? Which means that we end up with a highly concentrated inside of the cell for potassium versus less potassium outside because we've been sucking it in with this pump. Okay, so when we have these open channels for potassium, potassium likes to move out. Okay, so again, this is its preferred direction. What we're looking at here is the action of that sodium potassium pump, creating those different concentrations of sodium and potassium across our cell membrane. We're looking at open channels, showing us which direction each of these ions are going to move. And then we have an open channel. Okay. Bottom one is sodium in red, and the blue one up top is our potassium. We're thinking about that resting membrane potential of our neuron. Okay. So now we're going to draw together. Kind of imagine a cell that has an active sodium potassium pump. Think about the action of that pump. One thing I'm going to draw on immediately is we know that it's using ATP energy. This is a great example of primary active transport. To run this. Just noticed that sodium goes out. I'm going to tell you, you might not have noticed this or remember this when we talked about the action last time, but it's 3 sodiums that are being moved out. And for potassium, they're going in, but we're only moving in 2 potassium. Let's pretend we're starting with a cell that is just at 0 millivolts. We start with a cell at 0 millivolts and start running this sodium potassium pump. What do we think is going to happen to this charge? I put an action slide for this one, so who wants to answer here?
So negative.
Yeah, exactly. Right. They said this is going to become negative, right? So we're moving 3 positive charges out. We're moving 2 positive charges in. So essentially, what we're doing is exporting, so moving 1 net positive charge. So we're removing positive charges overall from this cell. Okay, removing more sodium, more positive charges than we're replacing with the potassium coming in. means that this membrane potential is going to start dropping down as we run that sodium potassium. Okay. Now. Ask some questions, upvote some questions. Check if we have one. So when we are thinking about our neuron, sodium and potassium are going to be our really important ions, the main ones. Calcium will come in at the end, but really the only major pump we're going to think about is the sodium potassium pump. So the sodium potassium pump runs stuff all through your body. And it has this electrogenic effect, this change in charge, in addition to those changing ion concentrations. So yeah, the sodium potassium pump is really the only one you need to understand this concept. So that's the one you want to understand for the exam. What you will need to be able to understand in terms of the movement of ions in general, so you are going to need to understand the electrochemical driving force and specifically the direction those ions are going to want to travel at specific values of the membrane potential. Starting at the resting potential of -70, then also as our membrane potential goes up, it will, as we start to see neurons fire, then it's going to go down and even kind of way down. We're going to want to know how that changes, which ions want to come in and how badly. The sodium potassium pump, the only pump, we do want to understand the movement of the ions that we talk about, but we're going to be specific in this unit, just specifically the ions that we need for understanding how neurons work. So it's mainly going to be sodium, potassium, and calcium. So determining those equilibrium potentials, we want to be able to think about the potassium ions and the sodium ions. We know a membrane potential in general exists because there are different accumulations of positive and negative charges inside the cell versus outside the cell. And overall, we have more negative charges inside the cell, which is why our cell is starting out at -70 millivolts. All cells have a resting membrane potential. We're going to use -70 over and over again because that's our resting membrane potential for neurons, and letting our neurons fire, send signals is really how we control our body. Okay, so that's going to be our most important resting membrane potential. But it is true that other cell types do have other resting membrane potentials. We're just not going to focus on them in this course. This is the real reason we care about resting membrane potential, is because we care about how nerves work. The resting membrane potential of our neurons is about -70 millivolts. When we're thinking about those equilibrium potentials for potassium and sodium ions, we know that potassium is at -94 millivolts, sodium is at +60 millivolts. Those are numbers I'm going to keep repeating because you are going to want to remember those. So to determine our resting membrane potential, right, we need to know a little bit about the ion concentration gradients, and we need to know something about how permeable the membrane of our neuron is to the ions. And this is gonna bring those ion channels in that we looked at on that picture. So this slide is just summarizing for you a bunch of the words that we're gonna see that involve the word potential, because it can get a little confusing. So I'm gonna circle ones I think will be the most important for us. Okay, so the membrane potential is always Vm. This is the difference in voltage across that plasma membrane. Okay. So when I tell you the cell is at -70, that's a membrane potential. The resting membrane potential is just being a little more specific. We say resting membrane potential because we're implying that we expect that membrane potential to change, which we do in a neuron because the whole way they're going to signal to each other involves changes to the membrane potential. The resting membrane potential is just like a normal membrane potential, but it's specifying that the cell isn't doing anything in particular right now. It's not firing. In the future, we're going to talk about graded potentials. So this will be important later on. These are going to be small little local changes to the membrane potential. We'll talk about them in specific later. We'll talk at length about the action potential, which is going to be a really big change in the membrane potential that occurs in a very specific way, in a very specific pattern, goes to very specific levels in a specific order. So that's going to be how our neurons fire. The other thing that we're talking about right now, as talked about a little bit already, is that equilibrium potential. Okay, so we know that at this point, our membrane potential, that charge inside the cell, counters our chemical driving force. So we have our EDF and CDF equal in an opposite direction. And that's the point at which that ion is stable and there's no net movement on the ion. Ion is at equilibrium at that specific membrane potential when it has that value. That's just teasing apart some of those terms. So our sodium potassium pump and how that relates to our equilibrium potentials and our temperature. So we just saw that it is electrogenic, right? So we're pumping 3 sodium out, 2 potassium in. So in total, we're exporting 1 charge. So we're going minus, minus, minus from the inside of the cell every time we run that pump. So 20% of the resting membrane potential, so like of that -70, a certain portion of that is due directly to the fact that we're pumping out all those sodium ions. Right? So directly due to the fact that we're removing those positive charges from the inside of the cell. The rest of that -70 value, the rest of that membrane potential, is also due to the sodium potassium pump, but in a more subtle way. Okay. So the rest of the membrane potential is the effect of the fact that we're producing concentration gradients. So the rest of our resting membrane potential is happening because we have a gradient on sodium. We have a high concentration of sodium outside the cell, a low concentration of sodium inside the cell, which we just set up with that sodium potassium pump. And we have the reverse for our potassium ion. We have low potassium concentration outside the cell, high potassium concentration inside the cell. Those concentrations are going to set us up for the rest of our resting membrane potential. So the rest of the way we get to that -70. So when we're thinking about our typical neuron, it's permeable to both potassium and sodium, okay? But it's 25 times more permeable to potassium. So what we're saying, when we have this membrane, ions cannot cross our cell membrane on their own. They have to go through a protein, specifically These ones are going through channels here. Okay. So for every one sodium channel we have, going out on the top this time, but I'll keep the colors the same as we had in that second slide. So for every one sodium channel, we have 25 potassium channels. So they are everywhere. I'm not going to draw 25 of them. That's why your book keeps just drawing 3. It's just indicating that we have that greater ability for potassium to move because of the presence of all these potassium channels. So we have potassium channels times 25. For every one sodium channel, we got 25 potassium channels. This means the potassium is easily able to move across this membrane, at least compared to sodium. Right? Both of them need a protein to go through, both of them need a channel to go through, but they need a channel specific to that ion. So potassium basically has more doors for, in this case, escaping. Other ions that exist around the cell, right? So outside the cell, we're going to have collections of sodium and chloride primarily. Inside the cell, you're going to have a bunch of high concentrations of potassium and some organic anions, some negatively charged things that are longer and more complicated. Other anions. So this is showing specifically what's highly concentrated in these locations. They do exist across both sides. Brings us to our next question. Right, so just said that we have high membrane permeability to potassium. We have a higher membrane permeability to potassium at our resting membrane potential. What is that going to mean for the movement of our ions? Take another couple seconds. Few people who don't want to vote right now, but let's take a look at where we are. Okay. Cool. All right. So our correct answer here is that we will have more potassium leaving the cell, so greater amounts of potassium leaving the cell than we have sodium entering the cell. Okay. So to figure this answer out, right, we would first need to know what direction these ions want to go, right, which we set up earlier, right? So we set up that our electrochemical driving force for potassium points out of the cell. Our electrochemical driving force for sodium points into the cell. potassium is gonna want to leave, and sodium wants to come in. Reason we have different amounts of movement, actually not because of the force on those ions, like its magnitude, its size, has to do with that permeability. So potassium is better able to move because the membrane is more permeable to it because of all of those extra channels. Potassium can leave the cell more than sodium can get in because sodium doesn't have that many channels available. The force for sodium is actually stronger than the force for potassium. But because we have all those potassium channels open, so many more of them, potassium is leaving the cell more than sodium is entering, at least at the resting membrane. Where do we move on? Questions about this question? When we're setting up these equilibrium potentials, we can think about starting with our imaginary little cell that starts at 0. Okay. We start at 0 millivolts, but we start with a high concentration of potassium ions inside the cell due to the action of the non-pictured sodium potassium pump, right? So setting up our gradients, our sodium. We end up with a high concentration of potassium inside the cell. When we start at 0, there's a force for potassium to leave because of that chemical concentration, right? So it has a CDF, a chemical driving force, to leave this cell. Okay? It starts up that movement of the potassium. As this progresses, potassium is leaving the cell. The inside of that cell starts to become negative. Okay. As the inside of that cell is becoming negative, we start to remember that negative charges attract positive charges, right? So opposites attract. So as the cell becomes negative, we start to have an opposing force to that chemical force. We start to have another thing that we have to take into account is that electrical pull for potassium to come back in, right? So we start to have an EDF, an electrical driving force, move in. Okay. But our net movement is still out at this point because that chemical driving force is bigger. Chemical driving force is stronger than the electrical force here. But essentially we're slowing down that escape of potassium as that cell becomes negative. Now, if we were to reach our equilibrium potential, the point at which this cell is so negative inside that electrical force on the potassium ions pulling them in is the same size as that chemical driving force wanting them to spread out and reach equal concentration. You have to get to negative 94 millivolts before those two forces are equal and in opposition, and we see no net movement. Okay. That was how we would set up the equilibrium potential of potassium. That's what's going on. Gives us our equilibrium potential definition again, where we have chemical and electrical driving forces that are opposite in direction but equal in magnitude. Reminder that the ion is at equilibrium when there's no net force, so no electrochemical driving force, it's 0 for it to move across the membrane. Chemical force is equal to the electrical force, but in the opposite direction, so negative. We're going to do the same thing for sodium now. We're going to start out with a hypothetical cell that is permeable only to sodium. Okay. So hypothetical cell permeable only to sodium. We set it up. Well, let's pay attention to the sodium, right? So we're gonna have high sodium outside. Lots of sodium outside. We now know that this is because of our sodium potassium pump. And no sodium in. Our concentration gradient here, our chemical driving force is for sodium to go into the cell here. Chemical driving force, just in that high-low direction for that gradient. That's where we start out. So our driving force beginning is just the same thing I just drew, but prettier. Okay, so we have our sodium ions outside. We have a chemical force moving in. Okay. If we have no charge inside that cell, we have 0 millivolts, there's nothing opposing it yet. Okay. So just like in our potassium, if there's no charge inside the cell, we don't have to think about the electrical part. However, as sodium diffuses into the cell, it becomes more positive, right? Because we start to collect those positive charges. So it would go up and up and up. As the inside of that cell becomes positive, like charges repel each other. So we have a positive inside of the cell, a positive sodium ion. It wants to get away from it. Or sorry, the sodium positive charge wants to get away from the positivity of the inside of the cell. So we start to build that electrical force for sodium to leave. Okay. So here in this drawing, that electrical force is still smaller than the chemical force. Hasn't gotten that big yet, so we'd still have a force for sodium to move in. It would just be slower. Until we reach equilibrium, at which point the two forces are equal and in opposition. So what has happened is that the inside of the cell has gotten so positive at positive 60, that that's a big enough of a push on those sodium ions, telling them to leave the cell, that even though we still have a chemical gradient, right, this electrical force is equal and in the opposite direction to the chemical force. So we're again at equilibrium, but we have a different equilibrium potential, a different charge inside the cell, because there's a different chemical driving force that we're opposing. The concentration of sodium and potassium is different. Okay? We set it up differently with that sodium and potassium. So we have our forces acting on sodium. We have that chemical force acting on sodium to be in. The electrical force, as we become positive, not at our resting membrane potential of -70, but as we get to that equilibrium potential of positive 60, that positive charge inside the cell pushing sodium out. So initially, we have a strong force for sodium to move in because of that strong chemical force and that relatively weak electrical force. But as that electrical force increases, because we're getting positive, more positive, more positive, more positive, eventually we reach equilibrium. Okay. Question break number 2. So go ahead and put in your questions. So when we're talking about neurons, we're not quite there yet for their shape, but yeah, we're just going to be doing a typical normal shaped neuron. At this point. Okay. Yeah. If we are at the equilibrium potential, Yes, that means that there is no electrochemical driving force, or it is equal to 0. When we use the word equilibrium, generally, what we mean essentially is that something is equal to something else, right? So equilibrium potential is referring to that membrane potential. It's at equilibrium. The forces on the ion are equal. If you talk about equilibrium in a chemical reaction or something, that means you find the chemical driving force. The chemical driving force, all you need to look at are the chemical concentrations. So that's that movement from high concentration to low concentration. So to find the chemical driving force, you figure out where you have more of that ion, where you have less. The chemical driving force is going to point to wherever there's less of them. So our chemical driving forces, perfect. Lead in, right? We set it up by creating high concentration of potassium ions inside the cell, high concentration of sodium ions outside the cell. So our chemical driving force always goes from high concentration to low concentration. So we're going from high potassium to low potassium. We got here. So that's how we know that our CDF, the chemical force for potassium, goes from inside the cell to outside the cell. Versus for sodium, we have a high concentration of sodium outside the cell. We'd have a low concentration of sodium inside because we've been pumping them out to the outside of the cell with that sodium potassium pump. So we go from high to low. So that's our chemical force for sodium. So that is the setup when we're setting up our resting membrane potential. Talked about how we would get to the equilibrium potential of each of those ions, potassium and sodium. Okay. So what we want to realize is that both of those things are going on at once. Okay, so potassium is leaving the cell, dropping that membrane potential down every time it leaves. Sodium is entering the cell, raising that membrane potential every time it enters. But this membrane potential, and this membrane potential is affected by the fact that we have a membrane that's more permeable to potassium. Right, so for every 1 sodium that gets in, 25 potassium can escape. So this is why at rest, the resting membrane potential, we have that -70 value, because all of that potassium permeability is creating a resting membrane potential that's closer to potassium's equilibrium potential, whereas potassium is the one that our electrical forces then develop. Then we change the speed of the flow, but they're all in the same direction. So this is just reiterating stuff that we've already covered. Okay. And eventually we reach a steady state where the inflow of sodium is balanced by the outflow of potassium. This happens at -. So that's where we will leave off